Last time we started talking about the line detection by Hough transforms. We said that one solution for line detection is template matching, trying out all possible line positions on an image, then testing if any of them contains enough number of edges. We said that this is too expensive. We don't have to do that. Even if we have only a handful of edges on our images, we have to test everywhere. This is not good. Instead, we said that let's use a voting scheme, a popular method in computer vision to find such nice structures like lines and circles and ellipses. A voting scheme. We are going to do this. We know that this is the formula for a line, and for each edge point on our image, it should have an x and y position, and for each x and y position of an edge, we are going to have a relationship between m and n in nm space. So that will be a linear relationship between n and m, and we are going to draw lines by incrementing the corresponding positions of those lines. And at the end of these iterations for all the edges, we will make a count. And I think this was one example. We said that one point is here, this blue point. The other one is there. Okay, so we have two edges in our image. And I like to find the line that goes through these these two points, these two edges. That is a dashed line. But I know that all the lines that go through this point will correspond to, when I write this equation, will correspond to this line in the mn space. And similarly, all the lines that go through this point will correspond to this line in the mn space, and their intersections is 2 2. If I draw this line, y is equal to 2x plus 2, I expect to have this line. That was the idea. So let's say I have a a third point on this line, and all the lines that go through this point, I don't know what's going to be, but it's going to be probably like this. So it is intersecting again at this 2 2 point. Okay. So that was the idea of the Hough transform, and this mn space is going to be a accumulator space. Whenever we are doing this line drawing, actually we are incrementing the counters of that line, and that will be our counting operation. Here, this is m, this is n, and these are the counters. Okay, so I have two peaks. One is here, the other one is there. Okay, the mn value for one of the peaks will correspond to this line, and the other peak will correspond to this line. And you see there are some other peaks here too. Maybe this line here, this peak, the green one, it might be probably, maybe, I don't know what it is, but maybe it could be this one. It has much smaller number of votes compared to other ones. So you select the threshold, you say that Any lines that get more than 15 votes should be okay with me, and this algorithm works. And that was the summary of what we did last time. So, and we said that we don't like this solution much. Actually, the idea is nice, but the solution is not robust to some situations. Some problems exist. Can you tell me what kind of problems do you see with this approach, especially with this y is equal to mx plus n approach? You know this formula from your secondary school, right?
In this A figure, there is three lines, and the fourth one, the green one. If we have a lot of lines in um, intersection of red and blue, uh, our count our count will be not like this, I think.
If there are, you mean if there are many edges like these, is that what you are saying? Yeah, that's true. I mean, even for the human beings, it is not possible to pick the lines that with the highest votes. But if a line can go through any of these points, I am going to find it. Selecting the perfect line is okay with this one. But if there is lots of noise, yeah, it will be affected. But you don't have another solution. I am not talking about the problem with the voting. I am talking about this formulation. What is m? M is the slope, right? How does the m change? What is the range for m? M changes from it changes from
Negative infinity to positive infinity.
yeah, it changes from negative infinity to positive infinity, especially for lines that are like vertical, it is infinity. So how am I gonna vote for infinity in this space, right? That's going to be a problem. That's going to be a problem. And the uniformity is another problem. I mean, the lines that are close to this angle will have very large or very small m values, okay? But but the lines that are close to the horizontal will have values that are concentrated on the zero value. Okay, so this infinite thing is not a good thing. And since I am incrementing a space, I need a accumulator, a counter buffer, a two-dimensional buffer. And that two-dimensional buffers, the two-dimensional buffers bounds cannot change from minus infinity to plus infinity. Those are going to be all problems. That's why we don't like this mn space. Mn space is not a good thing. Okay, so we need to switch our formulation. We need to use something else instead of using this rectangular coordinates. We are going to switch. Okay, so these are the problems. Both m and n can get very large. Okay, when what happens to m when x is constant is infinity? We don't like it. So instead of using this, we are going to switch to polar coordinates. Okay, polar coordinates. There are many ways to represent a line. A line can be represented using just two numbers. Okay, it is either mn in the mn space, or in the polar coordinates we have a formulation like this. Maybe you had seen this before, maybe you did not. It is okay. If I have a line like this, okay, I can represent this line by these two values. You take the closest point to the origin. Okay, this is the closest point to the origin. Okay, this distance is rho. This is rho, okay? This is rho. This is one of the parameters, and you take this angle. You take this angle, and this angle is theta. Theta and rho are our two parameters to represent the line. If you use theta, rho and theta space to represent a line, this would be the formula. Okay, you for each point on this line, any point on this line, this point or this point or this point or this point, doesn't matter, any point on that line has to satisfy this equation: x times cosine theta plus y times sine theta should be equal to rho. Okay, so what is the advantage of this formulation? The advantage is this. Theta can change from 0 to 2 pi, or maybe from 0 to pi. Okay, so it is nicely bounded. It is nicely bounded. Let's talk about this on this image. Okay, if this is 0 0, okay, let's say I have a line like this. So what is the closest distance? The closest distance is this one. And what is the value of theta? Theta is 0, so this is fine. How about this one? How about this one? This one, what is the closest line? Okay, it is here. So rho is this, and theta is this angle. So it is theta here. So I can do that. So theta can change from 0 to pi, no problem. Theta can change from 0 to pi. How about rho? What would be the largest rho number? If my image is m by n, what is the largest rho number? Smallest is 0. What is the largest? So this is the range for
the greatest value of rho, and if we think there is a line that is far away from start of rho point, it has to be in the line and it has to be in the circle. Yes, here, and its hypotenuse.
yeah. So this could be the farthest rho, right? This could be the farthest rho. So rho could be between 0 to square root of m squared plus n squared, right? So the thing is, what I'm saying is that we are not talking about the infinity numbers anymore, like the mn space. We are talking about nice numbers from 0 to pi, 0 to this number. Okay, so this is a good space. So let's do our voting in this space. Let's do our voting in this space. That's going to be nice. And this is our algorithm. It looks complicated, but it is not actually. Let's look at it. If our input is E, okay, E is an image, but it's a binary image. Okay, E is an image, but it's a binary image. Let me try to, can I use where? Okay, okay, I'm going to do it here. E is a binary image of size m and n. This is image E. So we have these edges marked on it. So I did the edge detection. For each edge, I mark its position with a 1. All the other points are 0. So it's a binary image. So E is a m by n binary image in which each pixel Eij is 1 if it's an h pixel, 0 otherwise. Okay, so E is our input. And as the data structure, we are going to do this. Let rho d and theta d be the arrays containing the discretized intervals of rho and theta. So rho d and theta d, let me draw them here. Rho d is a one-dimensional rho d, and theta d is another one-dimensional array. These arrays will contain the discretized, uniformly discretized values of rho and theta. Okay, so the value is closer to 0 here, and this value is going to be square root of m square plus n square. Okay, and the rest of them is and the rest of them are there. And for the theta d, this is going to be 0 value of 0, this is going to be value of pi, and this is going to be value of pi over 2. Okay, so these are the discretized, okay, values of rho d and theta d. And what are their sizes? Their sizes is there are r elements in it and there are t elements in this one. R and theta, R and d, okay, R and t, sorry, are two system parameters that we are going to determine them. So what's a good value for t? A good value for t maybe 90, okay, maybe 100. So we are dividing our 0 to theta interval into 100 intervals. And 0 to r, okay, this one, maybe just to be compatible with this one, maybe this one is 100 too. So it depends on values of m and n. If an m and n are 100 and 100, maybe this one should be around 150. So for each pixel, I am assigning a box. Okay, so in this case, each of these values are, why can't I write it? Each of these values are, these are delta rho, and this is delta theta. Okay, so t times delta theta is pi. Okay, good. So that I discretize, okay, so I have rho d and theta d, the arrays contain the discrete in terms of rho and theta parameter spaces. Rho is between 0 and s, theta is between 0 and pi, and r and t respectively the number of elements. The first step of the algorithm, discretize the parameter spaces of rho and theta using sampling steps delta rho and delta theta, which must yield acceptable resolution and manageable size for rho d and theta d. Okay, so how do I choose this delta rho and delta theta? Again, it's a design issue. If I choose them so large, my resolution will be very low. So whenever I find a line, it may not fit exactly the edges. If I choose it too small, then my resolution will be good, but my tables, my arrays will be too high. So something in between. And finally, our accumulator, that is our voting space. It's a two-dimensional array. Its size is r columns and R columns and T rows. RT. And this one is the counter. So each element of this matrix is a counter. So initially these values are all 0. I am going to do my voting on this space, on this matrix A. Okay, so let's start our main loop. Number 3. This is our main loop. Okay, for each pixel Eij, for each pixel Eij, such that Eij is 1, I am running a loop. H is running from 1 to T. Okay, let's take a pause here and let's go back to our formula here. How do you draw a line using this formula? How do you draw a line using that formula? Can anybody tell me?
The row formula?
From the what formula? Yeah, using the row formula, yes. How do you draw a line?
Now, we have the edge points, right?
We have row and theta values.
Ben birinciyi edeceğim artık.
Yeah, I already explained. So I am trying to make you repeat what I did.
Okay. So we find when we plug in the row and theta.
You exactly, you put the theta and rho in. So you will say, for example, if rho is 10, it would be x times, let's say, cosine theta is, let's say, 1 over 2 plus y times sine theta is, if cosine 2 is 1 over 2, what is sine theta? What is 1 over 2? 30 degrees? Anyway, I am going to put 1 over 2 here again. So there is a relationship between them. But the thing is here is different. We don't have rho and theta values, okay? We don't have rho and theta values. What we have is x and y values, okay? I know x and y values. I don't know rho and theta. I am going to, in the rho and theta space, in the rho and theta space, I am going to make a voting operation. Let's say x and y are fixed. It is 10 and 10. Rho is equal to 10 times cosine theta plus 10 times sine theta. So how would you draw this? Is this a line? Is this a line between rho and theta? Remember previously we end up with a line on M and N, right? Is this the same thing? Is this a line between rho and theta?
No, it is not line, I think.
It's not a line. Why? Because yeah, there is cosine and sine thing, right? If I take theta as 0, cosine 0 is 1, sine 0 is 0, so rho becomes 10, right? So I found it. So I start theta from 0, I calculate rho. So when theta is 0, the rho value will be 10, so I found it. And I increment theta a little bit. Let's say theta is 1 degrees. In that case, cosine 1 degrees will be very close to it will be very close to 1, but it is not 1. And this one is going to be very close to 0, but not 0. So in that case, theta is going to be a little bit value and rho is going to be something like that. And I think it's going to be doing something like that. Right? So it's going to be a curve like that. If I complete all of my drawings, if I change theta from 0 to pi. So unfortunately, it is not a line anymore. Voting is more difficult. But I know that theta changes from 0 to pi, and rho changes from 0 to, that number. Okay? So in this algorithm, I am trying to do the same thing. Keep changing the theta and calculate rho. Okay? So that's what I am doing. For each pixel Eij, I know it's x and y position, right? For Eij, I and j are the x and y positions. I am running this loop. This loop is going to be our theta loop. Okay? So our theta is going to change from 1 to t. So I am going to take all these values from this position to this position. Okay? So this is my formula. I will do, if h is 1, I will get this value from theta d, take its cosinus, okay, take this cosine and multiply it by I, which is x, and then I will put h in again in this theta d. I will take that value, h, again it is 0, I will take its sine value and multiply it with j, and it will give me a rho value. Okay, so I got a rho value. So for each h, I got a rho value, but this rho value is not usable directly because in my voting space I need integers. Okay, so my first integer is h. It can change from 1 to t. The second integer should be from the row. So what I'm going to do is take this row, find the index k of the element of theta d close to row. So I am going to scan this array here, find the closest row in this array. Okay, let's say it is this element. What is the index of this element? It is k. So I will take it. And I will increment a k h by 1. Let's say it is this point. I will increment this point by 1. So I am running this formula in a way that I produce these h values which correspond to indexes of these theta values. Get the thetas there, calculate row, and for each row find the nearest row in this array and get its index. So I use this h and k index to increment the values of a, k, h. Okay, whenever this loop is done, that means that I am going to iterate over all the edges. Whenever this loop is done, I am going to go over all the edges. That means that my voting is done. I will go to this space, this row theta space. Okay, I will find the maximum. I will find the elements that are higher than some threshold value. Let's say anybody who has more votes than 30 votes should be okay. I will get those points. Okay, so that's going to give me just two integers. Those two integers are not my rho and theta values. So where am I going to find the rho and theta values? I am going to find those theta and rho values in these two arrays. And I go to those two arrays and I look it up. Okay, rho d and theta d. I look it up and I will say that these are my rho and theta values. And using the rho and theta values, I can draw my line on this on this image E, maybe it's going to be this one. So here, let's say this is the maximum. This one will produce a rho and theta. I can draw rho and theta like this. Okay, so this is the whole algorithm. This is the whole algorithm. Half lines. It makes a voting in the rho theta space. And unfortunately, in rho theta space, I cannot draw lines like that anymore, like in the MN space, because the relationship between rho and theta is not linear. Okay, but the nice thing is that we are bound by these nice zero and these nice small numbers, and my voting is much more reliable now. Okay, any
Can I
question?
ask a question?
Sure.
Well, this is very powerful half, half lines algorithm. I have two questions. One of them is after we run this algorithm and then we write it to A space. You say that this is not like a line. I think it's like a spring or a snake.
Yeah.
Why is it shaped like that on that space? Is it a reason for theta?
Well, I mean, it is the way we represented our lines. We are representing our lines with sine and cosine formulas, and those functions behave like that way. Previously, it used to be y is equal to mx plus n. If you fix y and x, m and n are dependent on each other, linearly. In this case, rho and theta are not dependent on each other linearly. I mean, there is no. I mean, it is direct reason. It is direct consequence of this formulation. The rho and theta are not linearly related. They are related using these trigonometric functions.
I think if you rotate this Q row space, it looks like a sinusoidal wave.
Well, both sines and yeah, of course, yeah, you could express this cosine using a sine formula, and it would become a sinusoidal wave stuff. Yes, that's how it be.
I have a question. In T space, T vector, we say that it starts from 0 to pi, but we have more than angles pi, it's 2 pi. Why didn't we choose 0 to 2 pi?
Well, to get 0 to 2 pi, okay. Let's go to this our regular coordinate system. Okay. What is the theta value for this line? It is 45 degrees, right? Is that correct?
Yes.
So this is 45 degrees. And what is the m value for this one? M value?
135.
M value. M, the slope?
Sorry, 2 minus 2.
Something like that, maybe, yeah. Minus 2 or something. Okay. How about this one? If I draw this one, so the theta value is 135. No, 100. No, it is 200 and 15, right? Is that correct? 180 plus 45, 225.
25, yes.
Yeah. So what is the m value for this one? It's the same. Actually, I mean the 45 degree theta and 225 degree theta is the same thing.
Now I understand, thank you.
Okay, but if we, let's say, if I have an image like that, okay, if I have an image like that, the theta value for this one and the theta value for this one, we like them to be different sometimes, because this one is from white to black, this one is black to white, right? So what is the theta value for this one? It is 0 degrees for theta value. How about this one? I like it to be 180, so that I can distinguish these kind of stuff. So this is called polarity. If you have polarities of the lines, then you could use from 0 to 2 pi. But if you don't have the polarities, if you don't want to have polarities, so you don't care if you are going from, if you don't care if your left side is black or white, doesn't matter, as long as it's a line, then polarity is not important. In our case, we did not assume that polarity is important, and that's what we did. Okay, good. Any other question?
I have a question. I'm sorry. Can you, after this slide, you draw a square image, I think E image, and well, yeah, here, before this.
You in this?
No, before this slide.
Before this slide?
First,
Yeah.
yeah, here. We say that here, the corner of the image, we have a green line and we have a row. We say that theta is there, the upside of the row.
Okay.
Well, yeah, okay. When if I think like this Cartesian coordinate system, theta is theta is upside of x and here downside of x. So I think I can tell what I say that theta is the opposite sides here. Why is it opposite sides? And why it is not?
Well, I mean, in images, our coordinate system, is here. It's 0, 0. And we don't have any minus signs for the pixel coordinates. Okay? So for convenience, I assumed it that way. And in fact, I mean, maybe I lied a little bit. Our theta could change from 0 to pi over 2 at most. Our theta cannot be 2 pi, right? It could be from 0 to oh no, am I not correct? No, I am not correct. Oh, no, that's true. So if I do this, right, so it's going to be like that, and our theta is going to be larger than that. Okay.
Thank you.
Okay, for the green line that I had drawn, so that will be the angle. So it is larger than pi over 2. So our theta can change from 0 to pi over 2, but I mean, what you are saying is that these theta values are negative theta values, but the positive theta values are not possible in this case. I change my coordinate system from our regular Cartesian system to image coordinate system.
We are thinking about this space.
Doesn't matter. If they are all negative, then I can use it as a positive number. Okay. Okay, let's look at this algorithm again. So what is the complexity of this algorithm? What is the complexity of this algorithm?
We are looking.
Depends on the parameter is discretization.
So give me the complexity in terms of parameters then.
Okay.
Let's say we have a total of, q edges. I have a total of q edges. Number of edges is q. And number of theta d's is r, and this is t. So definitely it is q times for each element of this, and there is this t, right? And I do this calculation directly. This O1. I need to find this index k, and I can maybe use a hash function to find it. It is easy to do that. So it is q times t, and I think that's it. And I increment it by 1. After that I come back and I would find the peak. So it is not much, order of qt. Good, it is efficient. It is efficient. Okay, let's see some experiments actually. I am going to, take this one.
Hocam, I have a question.
Okay.
Before to create p theta space, we found p value for each theta value.
We found the row value for each theta value, right?
Yes. But can we do the opposite? I mean, for each row value, find theta value.
Yes, you could do it, but you need to solve this trigonometric function, both of them. So you will end up something like this. You are going to say 10 is equal to 5 times sine theta plus 4 times cosine theta. So isolate theta. How do you isolate theta in this case? You need to figure out something here, right? So it's going to, I need to write formulas, and you need to take a arc sine or arc cosine of some value. So it is more difficult this way. Of course I could have done it that way, but going the other way is easier.
I have a question. I'm sorry. We said that Q is our edges.
Yeah, number of edges.
But we don't know the number of edges, so we have to find them. Is it right? So don't we have to search all E image? We have to search E image to find all Q values.
Yeah.
So we now we in this case.
So you are going to scan. So you are saying that it should be O Q T plus M times N. That's what you are saying. So you are going to scan the whole image, M and N image, and for each pixel, that is 1, I need to run this.
I am saying that while I'm starting searching and find an edge, and then go to T value, and then find R value.
But you are not doing you are not doing this for all the elements of E, right? You are doing only if it is one.
Yes, now I understand exactly.
Okay. And usually inside this, I mean, when I said find the index k, this will require a loop too. I mean, I said that maybe we can use a hashing to find it in O1 time, or maybe a faster search algorithm, log n time maybe. But this will be the dominant factor Qt. So it's not going to be so it's not going to be um, it's not going to be very, very expensive. So let's see some experiments. Let's look at this image here. Okay, this is our image, and these are all edge detected. Let's say this is my image. This is I m by n image, and these points are these are all edges. Okay. How many edges do I have? I don't know. How many lines are there in this picture? There are 8 lines, right? So 1, 2, 1, 2, 3, 4, 4 horizontal lines and 4 vertical lines. Okay, so what do I expect? Let's try to draw this row theta space. Okay, let's say this is row and this is theta. Good. So what is the row value of this line?
It is there are two left.
So if I continue this line, so if I do this, so it is 90 degrees, right? It is 90 degrees. Is that correct?
Yes.
So 90 degrees for that one. How about this one?
It is the same, but a smaller value of row.
Row, yeah, the row is okay. So I have 1, 2, 3, 4 lines with a theta value of 90. So let's say theta values of 90 is here. This is 90. But their row values are different. So I would expect that one of them is going to be here. The second one is here. Third one and the fourth one, right? 4 of them. So which one is this? Which one is this? Is it 1 or 2 or 3 or 4?
Just
One.
four.
One, I
Four.
think.
Yes.
Is it 1 or 4?
One.
Four.
Four.
4 has the highest, largest row, right?
Row starts from left top side.
So for 90 degrees, so what is the distance? It is largest. 4 has the largest row value, right? So 1 has the smallest row value. Is that correct? So this is 1. How about this one? What is this?
Three.
Now it's three.
3, 2, and 4. Okay, good. Okay, let's look at the others. Okay. How about this line? What is the theta value for this line? If I continue it this way, okay, continue, what would be the, okay, so this is the right angle.
0.
It should be 0, right? What did I, why did I make a mistake in the previous one? Our angles are 0, right, in the previous one. Did I made a mistake, right? Our theta values are 0.
Yes. Yes.
Yeah, exactly, because I mean, I am not looking at this one. I should have looked at this one. So our theta values are 0, so I am going to do this 1 and this. So this is 1, 3, 2, 4. Now the theta value for this one is 90, so I am going to do this one, this one, this one, and this one. So this is going to be, let's number them, 1, 2, 3, and 4. So it is 1, 2, 3, and 4. So this is what I'm going to see. Okay, these are the peaks. Of course, not only the peaks will have votes, all the others are going to have votes. And this is the voting space. Okay, this is the voting space. Okay, so what do I see here? I have peaks. One peak is here, another one, another one, and another one. Other peaks are here. You see the peaks, right? And this is the theta, and this is rho. Oh, no, 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 I made a mistake. I think it is just the opposite. It is just the opposite. This is theta, right? And this is rho. Maybe put rho in here. Why? Because I think this one corresponds to maybe 0 degrees and this one corresponds to 90 degrees. And I think in this case, maybe the upper part corresponds to larger values. I don't know. Okay. So as you see, each edge draws a nice curve on this image, and I get these peaks. Which one has the highest votes? Which one has the highest votes?
Fourth, horizontal, vertical line.
Yeah, this one. This green one, green 4 has the highest vote, and I think it is this one. So this is 4. And with the same 4, right, and the same orientation, and this is 2, and this is 3, and this one is 1. How about this one? What is this? I guess that one is,
Red 3.
well, it has a, so this one is 4, the largest row, and this one is 90 degrees, and what is the largest? I think this one is 4. I think this one is 4 again, and then 3, and then 2 and 1. Okay, good. Let's do some other experiments. Let's take out some part of the edges. I have this. Okay, so I remove some of the edges, so there are breaks, some occlusions. What do I do now? I do the voting, and it looks like my positions for the peaks did not change. Only they became a little bit. Their peaks are not that high, but still they are peaks. It works. So it is exactly the same peaks. So this Hough transform is robust against the occlusions or the breaks in the lines. Okay. Or if I add noise, again, I get the same peaks. Lots of noise and I get peaks like these. Okay. So Hough transform is robust against occlusions and this kind of noise. No problem, it works. Okay, good. Any questions? I am way out of my time for the first part of the lecture, but I am going to take some time. Okay, let's take 10 minutes of break. We will be here around 14:39. Selamünaleyküm. Sen neredesin? Annenle konuştunuz mu? Ne kullanalım? Okay, people. Nobody mentioned this, but we can make this algorithm a lot more efficient, a lot faster, because we assume that our input is a binary image, ones and zeros. But if you remember, when we do the edge detection, what we have is our edges, okay, our edges and their directions. Okay, edges are like that. We have the directions for the edges, like this. Okay, so when you make a vote in the row theta space, we actually know about the theta a lot. Okay, we actually know about the theta a lot. So what do we do? We don't vote for all the h values inside from 1 to t. We only vote for the theta value
You
that
are
we get.
talking, we don't hear you.
You don't hear me because I did not. I'm sorry. Okay. Now you hear me, right? Uh,
Yes.
the problem with this half line, it is nice, but we don't use the angle information produced the edge detector. If we have this E image, okay, we assume that these are all dots, okay, but as you remember from the Kenny edge detection, each edge has a direction. We say that this is the direction of the edge. Okay, these are the directions of the edges. We have directions like these. Of course, not all of them are perfectly aligned. Okay, some of them are like these, but approximately we have the edge information. So what do I do with this? When I make my voting, I don't vote for all the theta values. I only vote, okay, let's say I am voting for this. Maybe I can vote all the angles between this value and this value only for this part of the theta values, because I can make mistakes, right? So I don't have to vote from 0 to 180 in that space. I only vote for a small amount of theta values. Okay, so what am I gonna do in this algorithm? Instead of running a loop from 1 to t, I would run h from a small, let's say, first get the theta value from the edge, okay, find the most promising h value and run the loop from that. Let's say that value is L, so from L minus 1 to L plus 1, so only three values of the age range. So that will make our algorithm much faster. Also, our voting space will be much less crowded if we use a gradient angle information, which we should use because it is available and we found it. It is not perfectly reliable, but it is approximately provides a good value for us. It will make things faster and more robust. Okay, so that's the final thing that I will tell about the half line detection. Okay, any questions about the line detection? Any questions about the line detection?
Why don't we use homogeneous coordinate system?
What would be the advantage of homogeneous coordinate system for voting?
I don't know.
I mean, remember the homogeneous coordinate system for the lines is we can talk about the lines at infinity or the points at infinity. We don't have such a problem in this case because we are trying to find the line that is already visible on this image E, right? I am trying to find these three lines. and these are not the lines that are on infinity, or we are not talking about points at infinity. So homogeneous coordinate system would produce exactly the same thing, but we have to deal with this that third coordinate, and it will not gain anything, so we don't. Okay, it is up to us, I mean, to decide which coordinate system we like to use. These are all mathematical modeling of the observations that we do in the real world, right? I mean, whatever model works best, we use it. Cartesian coordinates doesn't mean that it is the ultimate coordinate system. Most of the time it is so convenient we use it. Newtonian mechanics doesn't mean that it is the ultimate model for all the moving objects in this universe, right? But most of the time we use it because it is good enough. And we know that it is not perfect. We know that relativity is not perfect. We know that quantum mechanics theory is not perfect. There are no perfect theories that we know, okay? So how do we choose which model to use? We choose the model that makes our job easier. That's what we do. And it looks like, I mean, up to now, there is no perfect model to explain everything. Some people say that there is. So universal theory of everything. Some people say that. Other people say that there is no such thing, and we couldn't find it. Okay? So if you ask why didn't we use that model, we don't use it because it doesn't make our job easier. That's why we didn't use it. Doesn't have any advantage. How do you represent a real number? How do you represent a number, not number one? I represent a number with this real number stuff. Somebody has invented, and it's good enough. But somebody else said that why don't we represent each number by two-dimensional vectors? Okay, each number should be and 7, 2, 1. So what is the advantage of it? People couldn't find the advantage of representing numbers with two-dimensional vectors, and unless somebody found that if I represent it with two numbers, I can solve polynomials of third or fifth degree. I can find their roots, and we are going to use it. So they call it like a plus bi complex numbers. So each number is now represented by these two a and b values, two-dimensional numbers. So for many real life work, a is enough. A is enough. Just one number is enough. But if you are doing some polynomial stuff or some other frequency stuff, representing each number by two element vectors has many advantages. That doesn't mean that complex numbers are the ultimate representation of the countable stuff. No, it is not. There are better ways of representing things depending on your application. Okay, read about the history of the complex numbers. Why they had chose to use it and why they were not using it. Okay, let's go back to our class again. Hough line detection. As I said before, we like this formula from our high school years or from our secondary school years, and we didn't use this, although we didn't use it for voting in the Hough space. It was a good start. Now I'm going to use the same idea. So I am going to use the same idea to detect circles. X minus. Okay, how do I represent a circle in a closed formula? It is this one. So this one, to represent a circle, okay, to represent a circle, I need three numbers, A, B, and R. Okay, so if this is my image, if this is my circle, so A and B are this, A, B, and R this, right? So three parameters for a circle and two parameters for a rho and theta for a line. I know that, okay? So let's look at this one. That means that for the circles, if somebody gives me a image E that contains only the binary edges, then for each point x and this is y, right? Okay. For each point x and y, I can make a vote on this three-dimensional space A, B, and R. Okay. So three-dimensional spaces are difficult to deal with. Two dimensionals are too difficult to deal with for most of the time. How about this three-dimensional spaces? I don't like it. So maybe I can play some tricks and I can drop it down to two-dimensional space at a cost of something that I can ignore. Maybe I can solve. This is what I am going to do. Okay, half circle. If somebody gives me something like this, if you do the edge detection, what kind of edges I am going to get? I will get edges, let me use different color. I am going to get edges like this, right? Also, I am going to get many edges from the other parts of the image. After I do the voting, I expect to find the center of this penny and find the R, okay? Find the circle. Like this. Half circle detection. That's what I'm going to do. Again, we start with this. X minus a squared, y minus b squared, etc. Okay. If I use a parametric, we don't like this one because this includes three parameters. I like to do the voting in two-dimensional space. Okay. So I'm going to switch to a parametric version of this formula. This is the closed form formula. This is parametric. Okay. So what do I have here? Cosine. Let's try to do this. Again, this is our space. This is 0, 0. My parameter is now theta. Increase theta from 0 to 2 pi. Okay. Increase theta from 0 to 2 pi. If theta is 0, what do I have? If theta is 0, cosine theta is 1 times r is r, x is a plus r. Let's say a is this, a plus r is this. So I found it, this point. How about y? Y, okay, it says that sine 0 is 0, times r is 0. Okay, y is b, so this is like a and b, and this is my first point. Okay, if I continue this way, increase this theta, every time I calculate a new point, and I end up with this circle. Nice. Okay, so instead of using this formula, I am using this formula. Good. And this is R. Okay, and the theta is not part of the formula, right? Theta is not a parameter. We use theta as a parameter, as a variable to calculate each point of the circle. So I still have AB and R as our parameters. Let's try to eliminate this R. How do I eliminate this R? I would say R is equal to x minus a over cosine theta. Right? R is that. So I would replace this R with this one. So what I would get is y is b plus x times a, okay, times sine theta over cosine theta. So I am going to get 1 over tangent here, right? 1 over tangent. If I do this math all the way, I am going to get this. B is equal to a times tangent theta minus x times tangent theta plus y. So as you see, there is a relationship between a and b. I know x and y. I know this one. I know this one. Theta changes from 0 to 200 and 360. I know this one too. So I found a relationship between a and b now. Okay. So a and b, I don't know. So by changing theta from 0 to 302 pi, I can make a vote in the AB space, and I can find the center of the circle. Not R, but the center of the circle. Okay, this time, since I eliminated R, I cannot find R with this formula, but I cannot find R with this formula, but I can find A and B. So my voting space will be AB space now. Okay. Luckily AB space is the same as my Cartesian coordinate system. It is the same coordinate system. Okay. Once I find A and B, I know I am in the same system. So this A and B is going to get the most votes. Okay, let's look at the algorithm. Okay, this is my formula. Quantize the parameter space for parameters A and B. So my quantization in here in this case will be automatic. Why? Because A and B lives in my Cartesian coordinate system. This is already my images. Okay, let's say my image is m by n. So our AB space will be m by n too. So this is easy. So my resolution will be exactly the same as the input image, and the number of rows and number of columns are the same. So that quantization will be very easy for now. And my zero accumulator array MAB, I will make everything to A and B. I compute the edges in the image and their angles. And for each edge point, I will increment all the points in the accumulator array along the line. What does that mean? Why did they say it's a line? I know X, I know Y. Where does the theta come from? I said that I'm going to change theta from 0 to 200 and 0 to 2 pi, right? Where does the theta come from?
If it's 2 pi, it has to be like a circle, so it may be the other point of the circle.
Other point of circle? I don't have a circle formula in my hand. I mean, the older formula I have is this. I know x and y from the edge x and y. Where does the theta come from?
From the sample
From the
points and edge points.
from the edge, right? For each edge point, okay, I compute the edges in the image and their angles. What's an edge? Edge contains x and y position of the edge, also the gradient angle and the gradient magnitude too. I am not using gradient magnitude, so I include this theta. So I know this theta, I know this theta, I know x and I know y. So it makes B is equal to, right? B is equal to A times some number plus some other number. So this is a line between A and B. So I draw a line in my voting space. I increment the elements of it. Let's try to see what kind of line it is. Okay, so I will let's say for this edge, okay, or for this edge, it is the same thing. For this edge, I know the theta, I know x and y. It say that draw a line along this line, draw a line along this direction. Okay, and if I am going to do the same thing, another one here. If for this one, another line. For this one, another line. Where do they intersect? They intersect at the center of the circle. But if I have extra edges like that, each one is going to vote like this. Their vote will introduce lots of noise in my voting space, but they will not intersect with anybody in a meaningful way. Right? They are not intersecting. They are not contributing to the center or anywhere else. Only these are contributing to the center. So this algorithm, after I am done, this algorithm is going to find the center of the circle. Doesn't matter what R is, it's going to find the center of the circle. That's called half circle detection. Okay? Any questions? If I wanted, I could have voted in three-dimensional space, and in fact, I think the OpenCV half circle detect is using the three-dimensional space. I could have done that, but this one is using just two-dimensional space to keep the things simple. Of course, it is not finding the R value of the circle. It's just finding the center. Maybe just after finding the circle center, it is easier to find an R, because in that case you are going to make another half voting to find the R itself after you figure out this A and B, right? So if you know the A and B, if you know A and B, for each edge point you know X and Y, right? Okay, you would put in there, or like I did before here. I know A, I know B, okay, and I know X and Y. Theta is already known, right? So I can make a vote. I can make a vote for all the R values, and I can find the R values. Okay, good. Any questions?
I have a question. This finds the perfect circles, but in the real world, all the circles are not perfect. How can we find the not perfect circles?
Well, if you do the perspective transform of a circle, you end up with an ellipse, right?
Yes.
So how many parameters does an ellipse have? It has the center, right? A and B. It has the longer R value and the smaller R value. It has 4 parameters.
Yes.
So you are going to vote in a 4-dimensional world to find the ellipse. So it is more difficult now, because now you are in the 4-dimensional world.
I have a question too. I think I missed theta part. Which angle is theta? I miss it.
Theta is the angle of the edge. Okay? Edge angle.
Is it gradient?
Yeah, that's where we get the edge angles from the gradients, yes. What is our gradient angle? Gradient angle is either this way or that way, depending on bright to dark parts, etc. So in this case, our algorithm uses the edge angle. Algorithm uses the edge angle directly. We did not ignore it like our first line formula. Okay?
Thank you.
Good. Any other questions? So as you see, if you have a closed form formula, like the line formula, circle formula, or ellipse formula, whatever you can run a Hough algorithm for it, as long as you have formulas like this. So as Efkan has asked, how about the ellipses? Ellipses have ellipses have 4 parameters, so it is a more difficult task, 4-dimensional space. Okay, and if you have quadratics, okay, it has more values, more parameters on it, and you are going to have a more difficult time to find the good answers. So, but in theory, Hough detection, Hough shape detection works for anything. Okay, so but that's for any shape that has a closed form formula. How about if I have such a shape? My shape is like that. Okay, I don't have formulas. My shape is like this. Okay, that's my shape. Somebody gave it to me, and I don't know any formulas about it. And I like to find this shape in my image. Okay, no formulas. I cannot say y is equal to something 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 x, then something something. No, I don't have it. I only have this shape. That's it. I don't have anything else. Okay, how am I gonna find this shape using the Hough transform? Somebody came up with this nice idea. It has some restrictions. But it works for these kind of shapes. It's called generalized Hough transform. Generalized Hough transform. This is what I do. I pick a reference point on this object. Let's say this point. Okay, maybe let me use a different color. This is my reference point. How do you select the reference point? Just an arbitrary point near the center should be enough. Okay, pick a reference point on the pattern object, and then I would compute the theta angles. Okay, I would compute the theta angles along the object. Okay, so this is the theta angle, let's say here. Let me use the green again. Take the tangent of the point here. Okay, and the line perpendicular to the tangent. Okay, and this would be my theta angle. So in a way that this theta angle is my gradient angle, you might say. Okay, so a point like that. How do I do that? So I would take and this would be my theta angle. Okay, so I calculate the theta angle for all the points around this shape, compute the angles theta I along the object, and then for each theta I store the distance Ri and angle phi I from the reference point. So I know this point, right? Let me use blue now. I know this point. I know this point, and I am going to find the length R to the reference point, also the angle phi to the reference point. So for each theta I store Ri and phi I. Let me try to write a better phi. Okay, so this is a pair. I can calculate the theta I very easily. Why? Because all I do is I found the edges on any place. Okay, that edge is going to give me a theta. Okay, that theta will be indexed, is going to be used as an index for the Ri and phi I. So this is the training phase. This is how I learn about the shape. So I am saying that this is my edge. For this edge I know the theta I. This theta I will produce me an Ri and phi I. And I'm going to do the same thing in here too. Theta I is going to produce me Ri and phi I. So I collected all these theta i's, and you might say that what happens if you have the same theta I for two different points, right? Could it happen? For example, this theta here is 90 degrees, but theta here is going to be 270, right? Theta here is 45 degrees, but theta here at this point is going to be 235. Okay, so any point on my object will have a unique theta value. That's why I can use that unique theta value as an index for Ri phi I. But of course there is an exception for this. This doesn't work for certain type of shapes. Can you tell me what kind of shapes are there?
I'm thinking a convex shape.
Exactly. If my shape is like this, okay, it's a concave shape. It's a concave shape, right? So the theta value here is same as theta value there, right? Also theta value here is same as theta value there. So for concave objects like this, concave, what is concave? You have angles like these on the object, okay? Concave shapes, it doesn't work. It has to be convex shape all the time. So this is a convex shape, okay? This one is a convex shape. This one is a convex shape. And this one is a convex shape. But the one that I showed you here is not a convex shape. This one works only for the convex shapes. Concave shapes doesn't work because this assumption of unique theta for each point does not work. So again, this is training phase. I learned about my shape. When it comes to the runtime, okay, in the search image, for each edge point, I have the edge points now, okay. This is my image. In my image, I have lots of edge points. Okay, I have lots of edge points like that. Let me put a line there. Okay, for each edge point, what do I have? I have x and y values of it. Also I have the angle. So I am going to use that angle as an index. I know the index, okay, I know the index. Since I know the index, okay, for theta I know that my reference point should be in this direction and at this length. So I am going to vote here. This one says that I am going to vote here. This one says that I am going to vote here. This one says that I am going to vote here. Okay? Each one knows their theta angles and their R values. And this formula gives me that. Okay? And generalized Hough transform works this way. And if you stay within the assumptions, it's going to work nice. No problems. That's called generalized Hough transform. And some people have implemented this on a real hardware and 3D world, okay, and it can locate these kind of cubes and etc. Okay.
Can I ask why the phi? How is the phi angle measured? On the
Let's go back
training?
here. The phi angle, phi is here, okay. What is phi? First, from this point to the reference point, I drew a line, okay. The length of that line is r. Also, I take the angle of that line with the horizontal line. That's the phi angle. So you are saying that from this point I need to go as far as r units. But what is the angle? How inclined I should be? You should be inclined with phi angle.
Okay.
So I am r away from the reference point in this direction, phi direction. If you see a gradient angle like this, you are going to go this ri unit distance along this line phi I, ri and phi I for each theta I.
I have a question too about this case. After we find, after we select L point and then green intersection point, and then we know R. For all points.
Are you talking about the training phase or the runtime phase?
First case I'm talking about.
Phase, you are talking about the training.
Yes.
Okay.
Yes. The horizontal line, are we while we are finding phi angle for all points in this circle-like shape, we are drawing a horizontal line and then find phi?
Well, no, you don't have to. I mean, the phi means that the angle between this line and the x-axis. So let's say this is our coordinate system, okay. If I extend this blue line, this is what you're gonna get. This is your phi. Okay.
We have only one horizontal line, and we are looking for. Okay, I understand now.
Okay, so this is called generalized Hough transform. This could be used for places where you don't have the closed form formula or any type of formula for your shape, as long as your shape is not concave, it has to be convex. Even if it is convex, okay, even if it is convex, you might say that, okay, remember, okay, you know that you know that I'm sorry, there was a connection problem. Even if it's a concave case, you know that these two, they have the same gradient angles. Okay, maybe you can put them in a hash table or something like that. Okay, and this one is going to make a vote and the other one is going to make another vote. Maybe when you see such an angle during the runtime, you may vote more than once. Okay, so this theta here and this theta are equal, right? So let's say my reference point is here. For this one, R is here. For this one, R is different. So you will have two R's and two thetas. So during the runtime, you will have two votes for this kind of objects. Okay, good. Question: is Hough transform rotation invariant, rotation insensitive? That means that if I have trained my Hough transform, my Hough tables on this object, if I rotate this object 30 degrees, can I still find it on my runtime image?
As you said before, yeah, we are looking for the gradients. So if we rotate this, gradient will change.
So this is not insensitive to rotation. This is very much depends on the rotation. That's a bad thing, right? That's a bad thing. So generalized Hough transform as it is not insensitive to rotation. You need to keep the same angle. Okay, good. But you can make a voting. You can make a voting in a range of angles. You don't store only a single number for each theta I, but you may keep a number of r and theta I values, phi I values for a single point to cover that rotation rotation ambiguity. Okay, so with some expense for such a space, you can achieve some rotation invariancy for the generalized Hough transform. Okay, good. So we started looking at the line detection with a simple formula. Then we looked at the circles. Then we said that Hough transform can do anything as long as you have the formulas for the shapes that you like to find. But we said that what if you don't have the formula but you have the shape itself? Then in that case it works too, and we kind of handled it with some restrictions. Now we are going to look at this case, deformable contours. I need, okay, this is a CT image, computer tomography image of the human heart. I need to find this inner part of the heart, this part. I don't know the shape of it because it is deformable, it changes shape. I don't know the shape. Like the Hough transform, I cannot say this is going to be your shape. Okay, it changes. It doesn't have a formula, so how am I going to find it? How am I going to find it? One thing is, I know that these are high gradient areas, right? The contour that I am drawing is a high gradient area. Gradient is high. This part is bright, this part is dark. bright, dark, bright, dark, right? That's one thing. The other thing is this green contour is smooth. Okay, it doesn't do this. Okay, it doesn't break. It is smooth and it goes through the high gradient areas. So there are methods that can do such a thing. Okay, this is a circle. Of course, circle doesn't fit anywhere here. Doesn't work. There are methods that can start like a circle by by deforming this circle to find such contours. There are methods of it. Let me show you. Let me show you. Can I click on this thing? I cannot. What's going? How am I gonna click on it? Or maybe I can. Can I do this? Okay. Not text. Select. Pan.
It's opened on the background.
Yeah. Okay. Good. So I think this is where I got it. Yeah. So there are methods doing this. You start with a circle, it starts deforming, okay? And once it finds the place it needs to find, it stops deforming. Okay? Look at this part first. Okay, it immediately comes and it stops there. Why it is stopping here? Because it is both smooth and it likes where it is. It likes that high gradient area. It doesn't deform after this point because it doesn't want to go in there because it's a high gradient area. Again, it's a high gradient area. It doesn't do a very nice, very high, very sharp corner there. It is both high gradient area and it is smooth, right? So we have these kind of methods. They don't need any initial shape. They don't need any closed form formula. Okay, and they are called deformable contours or snakes. Snakes. Okay, so let's take 10 minutes of break. After the break we will continue, and I will ask first. Let's after we come back, let's make a decision on the midterm date. I'm going to vote for next week, and I will ask you if you like to see this deformable contours or not. Let's be here around 15:38. Okay, 10 minutes of break. Okay, people. So these are the deformable contours or snakes. As I said before, they are used for localizing unknown shapes. They don't have any closed form formulas or the known shapes. They need some initialization. They are initialized at some position on an image, and they deform. After a while, they find the desired position. They used to be very popular some time ago, but nowadays nobody is using them. I have seen a deep learning based snake implementation, deep snakes, somewhere, and if you like you can look at it, but it looks like for some reason I don't want to talk about them anymore. So that's it actually. I mean, I think it is enough for you to know what snakes are and how they work and how they are initialized, etc. I'm not going to talk about them. Yes, Doğa.
You share your screen? I don't
Well,
see your screen.
I did not share my screen yet, but there is nothing to share. I mean, it is the
Okay, so
yeah. I shared it. Thank you. So deformable contours, as I said, I think that will be enough for me because I am getting late. I should start talking about uh, stereo vision, etc. Okay. Any questions about deformable contours?
I have a question about not general Hough transform, a circle, uh, half circle uh, detection.
Okay.
We in the formula we don't look to R value. So if we have two half two half circles, but they are in the same center, our uh, our half detector will find these two same center half circle. Yeah. Yes.
Like this. Okay. So this doesn't like a circle, but so if we have two circles, if you have two circles, remember how we voted. This part, this one, this one will vote like this. This one will vote like that. Also, this one will vote like that. This one will vote like that. So they are voting for the same center. So our algorithm did not find R. It says that there is at least one circle whose A and B values are this. Okay.
Uh, in this case, if we erase smaller circles left side and bigger circles right side, we don't have any circles, but our algorithm will find a center of a circle.
That's called the insensitivity to occlusions. Even if you have a circle like this, even if I have a circle like this, it will find it. It will find the center. That's a good thing.
But if we have uh, a, a smaller R value circle part in this, um, yes,
So it will find it, yes.
but it is not a circle.
It's part of a circle.
Yes,
It's part of a circle. I mean, it's like the half line detection. If this is my image, if I have 1, 2, 3, and 1, 2, 3, and there are many other things, okay, this one will be one of the lines. This one will be a line, another line, another line, another line. Okay. So it's going to find it even some parts of are missing, and that's a good thing. And if you don't like the circle that is found by this one, you can always check it, and you can say that, okay, you found a circle, it looks like a circle, but I don't like it because many parts of this one is missing, as long as you have the circle in your hand.
Okay, now I understand. Thank you.
Okay, good. So I am going to skip this deformable contours. I am going to start our new chapter, which is geometry of multiple views. By the way, let's make a decision for next week's midterm. So I like to do my midterm next week on Monday during the class time. It's going to be a 2-hour lecture, 2-hour exam, sorry, 2-hour exam. And I will send you the instructions for the exam. You are responsible from all the topics that we have covered so far. But you won't be responsible from what I am starting right now. Okay?
I'm looking what we have learned about past topics. When I turn them, I see that all that's like that, all that's like that. I forget it. So how will the exam will be? Are we supposed to make some programming or?
No. There won't be any programming questions. There might be some problems, some calculations, and I am going to ask you some knowledge questions about what happens this and this. Maybe I might ask you some pseudocode. Write me some pseudocode that does this and that. But no, I won't ask any OpenCV related or Python related questions.
And mathematical things are very big in our computer vision lesson. And I'm frightened that I can't do anything in the exam.
Well, I am not expecting you to memorize all the formulas. I am not expecting you to memorize all the derivations that we did in the class. But you should know what a projection matrix means. You should know what homogeneous coordinates are, right? And you should know how a point is projected from the 3D world to 2D world. Okay? By the
Sir, can I ask a question?
Sure.
Do we have to open our cameras with exam?
Zafer, I did not get what you said. You have to what?
Do we have to open our cameras during the exam?
Yes.
Okay.
Okay. Um, Before we forget, let's look at what OpenCV offers for the Hough transform. Okay. These feature detection, there is this Hough circles and Hough lines. Let's look at the Hough line first. Hough line takes this image and it produces the lines, and it has this rho and theta input parameters. Let's look at them, what they mean. The distance resolution of the accumulator in pixels. So how do you represent? Remember that RT dimensions for the accumulator array. So you need to make a decision. How many in the row dimension, how many in the theta direction. Okay, that's one thing. Threshold is the how many votes do you need for this to be called a line. Okay, and for this SRN is multi-scale Hough transform. You do the Hough transform in more than one scale. First a small image, make a Hough transform, and after that you get the candidates and you make another Hough transform to make things more faster. Okay, and the SRN value, SRN and SNT value are for those. Okay, and minimum theta and maximum theta for the multi-scale Hough transform. These act as threshold values between these two scales that we are talking about. Okay, these are the Hough lines, and let's look at the Hough lines. Hough circle is this. You put the image and you get the circles back, and there are a few methods for the Hough circles. Let's look at what the methods are actually. Hough modes. Okay, it looks like they only implemented this Hough gradient. I don't know what the others are. And remember, with the Hough circles, your voting space is the same as the input space, but if you like to use a different resolution, you would use this DP. And what would be the minimum distance between the detected circles? You would give them this here. And these are the parameters for different Hough circle methods. And if you are using the Hough gradient like we did, it is the higher threshold of the two past Kenny edge. So it is doing the Kenny edge detection, and the first parameter is the parameter for the hysteresis thresholding. And the second one is the accumulated threshold. I mean, how many votes do you want? And minimum radius, maximum radius are good for constraining your search space. It looks like you have a fit ellipse function too. What is fit ellipse? I don't think that fit ellipse uses a Hough transform. Given the data, it just fits a single ellipse to that data. Yeah, a set of 2D points. So what is the difference between Hough transform and line fit? Can anybody tell me? The difference between Hough transform and line fit. Let's say this is my image.
One is regression, I think.
So what does that mean?
Minimum distance fit, like least square.
What is the difference in terms of results? Line fit and Hough transform. Line fit finds a line, Hough transform finds the lines, right? So what is the difference?
Hough transform is a transformation of the space so that we can see where which points we are interested in more clearly. And line fit, I think it will fit any data no matter what. I'm sure with an error result.
Yeah, for a line fit or circle fit or ellipse fit, you need the data. You would say that this is all of my data, and find a good fit for this data and say that, okay, your fit is this. Hough transform is not like that. Hough transform says that, okay, I have all of these edges. Find as many lines as possible. Okay. Hough transform says that, okay, I found a line here. I found a line. What's going on? I found a line here, another line there, another line there, and here's a line, and here's a line. How about these points? How about these points? What happened to those? Hough transform says that okay, they are noise. I don't know what happened. Okay, I don't know. I mean, it doesn't have to find anything to that one. But if you have set of edges like that, and if you have more edges like that, okay, if you say fit a line for me, it might fit something in between. Okay, so that's the difference between fit lines or fit ellipses with the Hough transform. So Hough transform offers a more general solution. Okay, good. So let me open this geometry of multiple frames thing. We are going to talk about stereo. Okay, we are going to make a introduction. Okay, so stereo is inferring depth from images taken at the same time by two or more cameras. By cameras, I am using human eye in this picture, left eye and right eye. I am sorry, this guy has a scary face. This is a synthetic image. This is not a real person. Okay. If you have a scene like this, your right eye sees these bowling what do you call them? Bowling dumplings, bowling
Pins.
pins. Okay, bowling pins from right, like that. Your left eye sees it from left, and your brain processes these two images, and it says that okay, this is the closest one, this is the furthest one. Okay, and one nice thing here is this. Look at this picture. Okay, if I have a point like this in the real world, the projection of this point will be here on that eye, and the projection of that point here will be on that eye. Okay, this point and this point. The light sensitive cells on the right part of the eye are fed to the same part of the human brain here. Okay, and this one does it here too. So what does that mean? If I am seeing the same object from left eye or right eye, the signals from the same object are transferred almost to the same location of the brain, so that brain can compare the images of two different eyes of the same object. Okay, so but the main task of stereo, as I said before, is to infer the depth of objects by looking two or more cameras, by looking the images of two or more cameras. And let's look at these two images. These two images looks like they are the same, but they are not actually. Look at the nearby objects. First of all, this object here on the right, I don't see it on the left. And this object on the left, I don't see it on the right. I don't see it. So these are two different images. Well, other than the missing objects, there are many other important differences. Let's see some of those differences. I see let's look at this one. I see this object. Let me use the red color. I see this object like this, and I see this ball like that, and there is a very small gap between them, right? There is a very small gap between them. They don't touch each other. But on the other image, I don't see such a gap. Okay, that gap is gone. Why? Because of the parallax, because of the angles of view of these two cameras. They are looking at the same scene. They are looking at the same scene from a different position. Okay, from a different position. Okay, look at the, okay, how many, let's say this is a 100 by 100 image, 100 columns and 100 rows. Okay, so what do you think this position is? So this is like maybe column number 50, right? Column number 50 on the left image. Let's look at the same on the left. Maybe this is column number 30. So there is a difference of 20 pixels from left to right. Okay. How about these two? How about the positions of this point here and that point here? Okay, it looks like this one is around 50 again, and this one is around, I don't know, 55. So the difference between these 2 points is just 5 pixels. And if you look at many other objects like that, you will see that the difference between the positions of the corresponding points will be large if the objects are small, if the objects are closer to the camera, and this difference will be larger if the objects are away from the camera. Okay, objects are closer, then this difference will be high. If the objects are away, the difference will be small. Okay, that's called disparity, and this is the corresponding disparity image. This is the corresponding disparity image between these two images. Disparity means, for example, here, this is a very bright point. Maybe it is around 60, intensity is 60, but when I look at this point, the intensity is maybe 10. Okay, so 60 means that this point is very close to me. 10 means that this point is not that close to me, it is away from me. Okay, so this is called the disparity image. So many times our main purpose from stereo is to extract this image out of these two images. You look at these two images and you extract this image, because the disparity directly gives you the depth information. Higher the disparity, closer the object. Okay, lower the disparity, further away from the camera, the object. Okay, so that's what we are gonna do. By the way, you may ask, why did they take such pictures? They take these pictures for testing some of the computer vision algorithms, stereo algorithms, and we are going to see these kind of pictures a lot in our lecture about the stereo. Okay, any questions so far about the stereo? Human eye does the stereo a lot, but stereo doesn't work for the far away objects. Stereo works only close by objects. It all depends on the baseline, and we are going to see it in a few minutes. Okay, so let's do some review of perspective projection. We did it before. Okay, I have taken these slides from this course. I don't know where I took them, and I think I am going to use many of those slides, and sometimes I am going to use some other slides from somewhere else. Okay, so remember, if I have a point in the real world that lives on this coordinate xyz, if I take a picture of that point corresponds to this small xyf. Okay, so the formula to derive x from xyz and y from xyz is this: x is f times x over z, y is f times y over z. This comes directly from the similarity of the triangles. You remember this, right? f is the focal length of the lens that we are using. Similarity of the triangles, that's it. Okay, we already know these. And the similarity of the triangles works for the x dimension. Okay, the ratio of this small s to capital S over ratio of this f over z. If we derive our formulas, we get this. And I do the same thing for the y, and we get both of them. We get both of these. Okay, but here is the problem: the fundamental ambiguity of the stereo or computer vision. Any of those color points would produce exactly the same position on my image, because if x is f times x over z, if I multiply x and z with the same k, I would produce exactly same x and exactly same y. Okay, so how am I gonna know the depth of those points? How am I gonna know x, y, z of those points by looking at this image? It is impossible. It is impossible. So this point could be either this one or that one or that one or that one or that one. I don't know. I don't know. Unless I introduce a second camera. First camera says that any point on this one will be P. But the second camera says that, okay, all the points that would produce the same thing for this P could be on this line. It cannot be anywhere else, right? This is what second camera sees. So whatever this camera cannot observe, this camera observes it. So what do we do now? What do we do to find the depth of that point? What are we gonna do? So somebody should say that, okay, this P is same as this P here. Okay, if somebody tells me that, then I would just draw this line. I would just draw this line, and I would just draw this line here, and this intersection would give me the xyz of that P. So somebody has to find the intersection, somebody has to find the correspondence between these two images. The correspondence between these two images. Again, we came to the correspondence topic. We came to the correspondence topic, and we have to find it. If I go to this picture again, previously, since I used my human knowledge, I knew that this point here corresponds to this point. I knew that, okay? I also know that this point corresponds to this point, okay? These all come from my common sense knowledge. I know these. I can establish these correspondences very easily as a human being. For the computers to establish these correspondences is not that easy. Okay, it's not that easy. Maybe you could do that. I mean, what would you do? You would run sift or surf or orb on this image, and you would run again sift, surf, or orb on this image, and you may run your flan or the brute force correspondence establishers, right? And if you do it that way, you should be fine. But that would not produce a dense disparity map for you, right? Because you are going to, let's say this is a 100 by 100 image, there are 10,000 pixels here and 10,000 pixels here. Surf is going to produce you at most 100 points and 100 points there too. So you will have at most 100 correspondences, but I need 10,000 correspondences to produce this image, disparity image. Okay, so running the regular correspondence algorithms that we did before will not work here. Okay, but the main idea here is we need to establish correspondence between these two images so that we can do this or that, rather that. Good. Okay, you got the idea, right? One nice thing about this picture is this. If I am going to find the corresponding point P on the other image, I need to look at only this line and nowhere else. The corresponding point of P cannot be here or there. Why? Because the point that produced this P should be on this line, and if I take a picture of that line is this green line, and that P cannot be anywhere other than this green line. Okay, this is called epipolar constraint. Okay, this is called epipolar constraint. And this epipolar constraint is very, very useful tool for us to restrict our search space, to bound our search space, to make our search space smaller. Okay, and luckily, maybe I shouldn't say luckily, okay, if I am going to find the corresponding point for this one, I am going to look at this line only. Okay, the corresponding point for this one, I am going to look at this line only. Understand? Okay, so for some reason they are in the same row because these images are specially created, they are pre-processed, and their corresponding epipolar lines are at the same line in the other image. Okay, good. So why stereo vision? Okay, it gives us very good advantage for finding the depth of points from the camera. Okay, and as I said before, human eye does the same thing. The same scary guy again. This is called the baseline. The difference between the centers of projection of these two cameras, 63 millimeters. On the average human baseline is 63 millimeters. Okay, not a very large baseline, but it's good. So this baseline is useful for estimating the depths of objects near to us. So comparable to this 63 millimeters. Okay, your two eyes from a stereo system. The right and left eyes see the world from slightly shifted vantage points. Like in fact, we can do a little bit experimentation with this in a few minutes. Okay. So key concepts for stereo. We are going to look at this concept of parallax. Then I am sure you know already about this anaglyphs. Okay. We are going to see what it is. Random dot stereograms and mathematics of simple stereo. Okay. Let's do this experiment. Okay, which camera you are seeing? This you are seeing this camera, right? Yeah. Um, Keep your thumb like this, close to your face, and look at your thumb with your left and right eyes. Close one eye first and the other eye. Okay. You will see that your thumb position changes a lot. The closer your thumb, more positional change happens in your left and right images. Left and right. Do the same experiment. Okay. But if you move your thumb away from you, the position doesn't change much. Okay. For the far away objects, I am looking at my monitor that is 3 meters away from me. Left and right are exactly the same. So that means that shift from left image to right image is not much for far away objects. So that depends on your baseline actually. If the baseline is large, then you can see the difference between two images even for far away objects. Okay. So again, the position for your thumb when the thumb is close to you changes a lot. That means that despite is a lot. Okay. So the human eye uses this a lot for you. And maybe we can do the same experiment with while we are traveling with a car, okay, at a high speed like maybe 100 kilometers per hour. Just turn your head, if you're not the driver, to the side of the road and look at the movements of the objects. Very nearby objects, they seem to move very, very fast. Far away objects, they don't move at all. In fact, when you look at the moon or the sun, when you are traveling like that, it looks like they don't move. It looks like they are following you. Okay? So, that's the effect of parallax again. Parallax is the perception of the near and far objects while the camera is moving or you are changing your camera view of angle. Okay, that's called the parallax. That's called the parallax. Okay. This anaglyphs, okay, they were invented long time ago, and usually we use these kind of glasses to see these anaglyphs. Do you have any of these glasses with you? I think I had one on my desk some time ago. What did I do with my glasses? I was keeping them. Can I find it? But even if I can find it, I won't be able to show it to you. I couldn't find it. I think I had them somewhere there. Okay, exercise for you. Next week you have your exam, but the other week you are going to buy a couple of these, okay, from your nearest Japanese store or Japan store, what do you call it? convenience store and buy them, and we are going to look at some images. Even if you can't buy them, you can do it yourself. Do this. Take these kind of blue and red whiteboard pens and find a transparent sheet covers like this, but it should be fully transparent, like not like this, and paint it with your red, some left part red and right part blue, and you can hold them to your glasses, and that's going to make a nice 3D glass. Okay, and we are going to look at these images next week. I am looking at, can I find, oh, maybe this one. Can I paint these? If I paint these and if I do that, it should work, right? Maybe this one? No. I will figure it out next week or the other week. Okay, the best thing is maybe you should buy just one or two of them. I think they are all available. So we are going to look at some images and we are going to try to explain why it works. Okay?
If we use only a camera, it wouldn't work, right? But we use, for example, two cameras, but different filters on it.
Well, you have two cameras already. You have your left and right eye.
No, but I was thinking about my phone. So, for example, instead of trying to maybe do that, I was thinking maybe if I filtered half of the screen to blue and
No, that doesn't work because you need two images, one for your left eye and one for your right eye at the same time. Okay? So these glasses, they will try to show you two images out of the same image. For example, this is a single image, okay? It has two images on it. One is a cyan color image, the other one is a red color image. So one of your eyes is going to see the cyan colored image, the other one is the red colored image, okay? And your brain will think that you are seeing two different images, and it will do all those parallax processing, and it will try to see a depth image, okay? And when we look at this after that, using those glasses, we are going to look at this one, okay? One of your eyes will see the cyan part, but no red part. The other one will see the red part, but not the cyan part. Okay? So that's the effect. So you are, by blocking some of the light from the world, one of your eyes will not see the red, the other one will not see the cyan. So in effect, you are creating this left and right illusion, left and right different images from the same image, Okay, I guess that's it for today. Next week you will have your exam, and I will send you the instructions for the exam in 1 or 2 days. I will post all the slides that I had used. I think I already posted many of them. Before I forget, let me post them now, right now. Chapter, which chapters do you guys think? Okay, I am going to post them anyway, like that. Where is my, okay. So, okay, that's it for today. I'll see you next week for the exam. There will be no lecture for the exam for next week. We will have our exam only.
Thank you. See you next week.
Okay, bye.
Thank you. Bye.
It looks like I have the grouping, and yeah. Okay, anyway, I am loading that.